Have you ever noticed why some planes have their nose painted completely black and others don't? For decades, almost every airline in the world did this. Then they just stopped. And now, weirdly, it's coming back again. So what's going on? Was it a style thing? A branding decision? Or was there something hidden behind that black paint that most passengers never even think about? The answer is way more interesting than you'd expect, and it starts with what's actually sitting inside the nose. Stay with me, because this one goes from World War II secrets to modern Airbus design, and it all connects through a single coat of paint. Most people think the nose of an airplane is just a pointy tip that makes it aerodynamic. It's not. It's actually a completely separate piece, and what's hiding inside it is one of the most critical instruments on the entire aircraft: the weather radar. That radar antenna sits right behind the nose, constantly scanning ahead, detecting thunderstorms, hail, heavy rain, turbulence, basically everything that could ruin your flight or worse. Without it, pilots would be flying blind into weather that could bring down an airplane. Now here's the problem. Radar works by sending out electromagnetic waves and reading what bounces back. For that to work, the cover protecting it cannot be made of metal. Metal blocks radar signals. It reflects them. That would completely defeat the purpose. So engineers built this cover out of fiberglass, a material that's basically invisible to radar. The signals pass right through it like it's not even there. This cover has a name. It's called a radome, a combination of radar and dome, and that term has been around since World War II. But here's where things get tricky. Fiberglass is great for letting radar waves through, but compared to the metal fuselage surrounding it, fiberglass is fragile. And where is it sitting? At the very front of an aircraft doing 500 miles per hour. Rain, dust, hail, ice, insects. Everything the sky throws at a plane slams into the radome first. The wall thickness is so precisely engineered that even a variation of 0.005 of an inch can start degrading radar performance. Too thick, and the signal weakens. Too thin, and the structure fails. It has to be exact. And that's exactly where the black paint story begins. During World War II, radar was one of the biggest military secrets in existence. Britain, Germany, the United States, and Japan were all racing to build systems that could detect enemy aircraft. And the need for radomes, those protective covers, is actually what drove the development of fiberglass as a structural material. The military needed something that could shield radar antennas from the elements while letting signals pass through. But early fiberglass radomes had a serious weakness. They couldn't survive actual flight conditions. One of the first major radomes was fitted on a B-29 bomber. On its very first flight over the Pacific, the aircraft hit rain. That's it. Just rain. And the fiberglass was completely destroyed. Rain erosion at high speed shredded it, and the entire radar capability was gone. That one incident changed everything. Engineers realized raw fiberglass simply couldn't survive high-speed exposure, so it needed a protective layer, something tough, flexible, and radar transparent. The solution was neoprene, a synthetic rubber that could be bonded over the front of the radome to absorb the impact of rain and particles at speed. And here's the key detail, that neoprene was naturally black. Nobody chose the color. Nobody sat in a meeting and decided on black. That was just the color of the material. Black rubber went on, and suddenly every aircraft with radar had a black nose. As commercial aviation boomed in the 1950s and 60s, airlines wanted something cheaper and more practical than constantly replacing rubber covers. So they switched to paint. But they couldn't just grab whatever paint was on the rest of the aircraft. Back then, fuselages were coated in lead-based paint, or standard across the industry for corrosion protection. But lead-based paint contains metallic compounds, tiny metal salts and oxides mixed into the formula. And when you put metal particles right in front of a radar antenna, they reflect and scatter the signals. The radar becomes unreliable, in some cases, nearly useless. Even the thickness mattered enormously. Anything over 12 to 15 mils, fractions of a millimeter, could drop radar efficiency from 90% down to 50 or 60. Pearlescent finishes, metallic flakes, completely off limits. So airlines were stuck. They couldn't use fuselage paint on the radome. They needed something with zero metallic content, applied extremely thin, that still protected the fiberglass from UV and weather. And in those days, the options were almost non-existent. Black paint turned out to be one of the very few pigments that checked every box. No metallic compounds, thin application, no radar interference. Cheap. So when airlines ditched the rubber, they replaced it with black paint. Not because they wanted black, but because black was essentially the only color that worked. And just like that, the black nose became the global standard. But once it was there, airlines realized it was solving problems they hadn't even thought about. The radome is a removable, interchangeable component. You can pull it off one Boeing 737 and bolt it onto any other 737 in the world. When a radome takes a bird strike or gets cracked by hail, airlines grab whatever spare is available, sometimes even from a different airline, and attach it on the spot. If every radome matched a specific livery, or one swap and the whole thing looks wrong. But if every radome is just black, pull one off, put another on, nobody notices. Back in service within hours. Then there was glare. On older aircraft with polished metal fuselages, sunlight reflected off the nose area straight into the cockpit. At altitude, that glare isn't just annoying, it's dangerous. It washes out instruments and reduces visibility during critical phases like landing. So airlines painted the area between the radome and the cockpit windows matte black to absorb sunlight instead of reflecting it. Same principle as the black grease football players put under their eyes, just at 35,000 feet. And finally, lightning. The radome is fiberglass, non-conductive. When lightning strikes the nose, it has no natural path to follow and would punch straight through to the radar antenna inside. Engineers bonded thin conductive strips along the surface to channel lightning safely into the metal fuselage. Some airlines, like British Airways, even applied special conductive black paint around the radome to continuously drain static buildup. So the black nose wasn't just about radar compatibility, it was solving 4 problems at once: radar protection, radome swapping, glare reduction, and lightning safety. No wonder every airline kept it for decades. But starting in the 1980s, paint chemistry went through a revolution. Modern polyurethane and epoxy-based paints eliminated metallic compounds entirely. No lead, no metal salts, no bronze flakes. These new formulas were completely radar transparent and thin enough to meet the strictest radome specifications. At the same time, radome materials got a massive upgrade. Advanced composites with Kevlar reinforcements and honeycomb cores that could handle rain erosion, hail, and UV without needing a protective layer on top. Once both barriers were gone, airlines saw their opportunity. The nose is the first thing you see when a plane taxis toward the gate. For decades, that prime real estate was wasted on flat black paint. Now they could extend their livery all the way to the tip. Clean lines, full brand colors, seamless design. One by one, the black noses disappeared, or so everyone thought. When the Airbus A350 entered service, people immediately noticed something distinctive on a sleek black mask wrapped around the cockpit windows. Aviation enthusiasts started calling it the raccoon mask. But this time, The black has nothing to do with radar. The A350 was the first Airbus with curved 4-pane cockpit glass, replacing the traditional 6 panes. This new design reduced drag and improved fuel efficiency, but created new challenges around heat management. The black mask absorbs sunlight and reduces cockpit glare, distributes heat more evenly across the window panes to reduce thermal stress, and conceals structural hardware underneath for easier maintenance. The design was so effective that Airbus adopted it across the A330neo, A321neo, and A321XLR. It's now essentially the Airbus signature look, so the black paint is back, but for completely different reasons than it started. And maybe the most interesting part of all is this: a coat of black paint on an airplane nose has been reinvented 3 separate times across 80 years. First as neoprene rubber protecting wartime radar, then as the only radar-safe paint available, and now as a thermal management solution on the most advanced commercial aircraft flying today. The color never changed. The reasons behind it changed completely. Sometimes the smartest engineering decisions aren't the ones that introduce something new. They're the ones that find a new reason to keep something old. If you learned something new today, hit that like button and subscribe. We break down stories like this every week, the hidden engineering behind things you see every day but never question. Until next time.